Welcome. This course covers the core components of AI agents, how specialized nodes assemble into one controllable system.
Unlike a single LLM call, an agentic architecture houses distinct specialized nodes that cooperate. The core map includes planner, executor, memory, evaluator, and tools working as one loop.
Data flows through perception, reasoning, tool execution, and state evaluation in a continuous cycle. A shared state vector carries history, goals, and working variables between nodes.
Modular graph systems stay flexible, while monolithic prompt templates become hard to control.
The underlying LLM acts as the brain inside specialized nodes, while code wrappers keep boundaries clear.
Failures such as tool errors can be caught and isolated so the full system state does not collapse. Section 1 Takeaways. Agents are composite systems, state flows through the loop, and modularity isolates faults.
Pause here. Nodes specialize for control, and state keeps the loop coherent. Now the quick check. Quick check after Section 1. Which statement best describes an AI agent architecture? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 2 focuses on the planner node, decomposing goals and choosing reasoning strategies. The planner ingests a high-level prompt, such as organizing a 3-city European marketing tour, and turns it into steps. Planners can follow one linear path or explore multi-path trees that branch and prune options. React interleaves thought, action, and observation, so planning stays grounded in results. Tree of Thoughts generates multiple reasoning branches, scores them, and prunes invalid paths. Plan and Solve builds a full plan up front, then tracks execution step by step. When a tool error appears, the planner can intercept it and update downstream subtasks dynamically. Dependency graphs show which tasks can run in parallel and which must stay sequential. Section 2 Takeaways. Planners decompose goals, choose strategies like React or Tree of Thoughts, and adapt to observations. Pause here. Pause here. Plans turn goals into work, and strategy depends on uncertainty. Now the quick check. Quick check after Section 2. What is the primary role of the planner node? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 3 covers the executor and tool interface that turns planned steps into real actions. The executor converts abstract planner instructions into strict API calls and environmental actions. Function calling sends a structured JSON schema with tool name and parameters to the executor.
Untrusted code should run in secure sandboxes, such as containers or micro VMs.
The executor can call external services such as search, CRM, or payment APIs and return JSON payloads. Deterministic validation checks argument types before invocation, for example, verifying an ISO date format.
When rate limits or timeouts appear, the executor can apply exponential backoff and retry safely. Raw API responses are truncated and formatted into clean observations for downstream nodes.
Section 3 Takeaways. Executors run tools, sandboxes protect hosts, and validation plus retries keep the loop resilient. Pause here. Plans need a safe executor, and observations feed the next turn. Now the quick check. Quick check after Section 3. How does the executor safely run untrusted code? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 4 covers memory systems, short-term context, long-term stores, and structured knowledge. Memory splits into short-term working context and long-term persistent stores. Short-term memory manages scratchpad observations, current task state, and recent message history. Long-term episodic memory stores past trajectories in vector databases for later retrieval. Semantic retrieval, or RAG, looks up relevant domain knowledge with top-K similarity search. Procedural memory retrieves specialized how-to workflows and learned skill routines. Knowledge graphs store structured entity relationships such as users, products, and orders. Good memory systems clean contradictory entries and balance semantic relevance with recency. Section 4 Takeaways. Short-term context, long-term episodic retrieval, and procedural plus entity memory. Pause here. Memory makes agents continuous, and different stores serve different jobs. Now the quick check. Quick check. After Section 4, what distinguishes short-term memory from long-term memory? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 5 covers the evaluator and reflection node for quality control and guardrails. The evaluator assesses whether tool output actually satisfies the current subgoal. In reflection-style loops, the evaluator writes corrective feedback when quality standards are missed. Deterministic verification runs compilers or unit tests instead of trusting model self-reports alone. In a critic-actor pattern, one agent proposes and another critiques against a rubric before release. Guardrails intercept safety violations, PII leaks, and unsupported claims before the user sees them. Loop detection catches repetitive ping-pong execution and forces a path change or termination. Low-confidence cases can escalate to a human review dashboard before continuing.
Section 5 Takeaways. Evaluators audit quality. Reflection corrects errors, and guardrails handle safety and escalation.
Pause here. Quality needs an explicit judge, and guardrails protect users and systems. Now the quick check.
Quick check after Section 5. What is the main function of the evaluator in a reflection loop? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 6 covers orchestration and state graphs that connect components into controllable workflows. State machine architectures treat nodes as functions and edges as conditional transitions.
A shared state object is passed cleanly across planner, executor, and evaluator nodes.
Conditional edges route high-quality results to the end node or send weak results back to the planner. Multi-agent topologies use a supervisor to route tasks to specialists such as coder, tester, or writer.
State persistence enables pause, resume, and step rollback through saved checkpoints. If the system crashes mid-run, the orchestrator can rehydrate state from the latest checkpoint.
A global monitor shows active execution pulses traversing nodes in real time. Section 6 Takeaways. Graphs define transitions, persistence enables recovery, and orchestrators manage multi-agent control.
Pause here. Graphs make control explicit, and checkpoints make systems durable. Now the final section check.
Quick check after Section 6. In graph-based orchestration, what controls node transitions? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
You completed a quick check after every section. You can now explain the planner, executor, memory, evaluator, and orchestration graph.
Congratulations! You completed core components of AI agents. Thanks for watching.